So in this video, we're going to look at the influence that b and c, the coefficients or the constants b and c, have on our quadratic function. So I'm just going to throw this into Desmos. I'm going to add my coefficients a, b, c. It's going to look like this. And if you notice again, those sliders are popping up. So we'll generate those in a second. There we are. And it says add slider. I'm going to add sliders for all of them. Okay, so this is where I have x squared plus x plus c, or well, c is equal to 1. So this is x squared plus x plus 1. And again, I'm also going to generate a copy of this and a table of values. Okay, so what I'm going to do is I'm going to set a as equal to 1. And then if b and c are equal to 0, just remember that this is actually just our generic quadratic function of y equals x squared. There it is. And now what I'm going to do is I'm going to add some changes to b. Okay, so let's use the slider and see what happens with b. So as I change the values of b, if you notice, as b gets larger, take a look at what's happening to your graph. So if we just focus on the vertex, you can notice that the vertex, as b gets larger, meaning that it is positive, your graph is moving left and then to the bottom of the, like, towards the negative x and y values. And as your b value is becoming more and more negative, your graph is actually moving towards the right and downward. Okay, so that's something that we can just kind of mention really quickly. So I'm just going to take a screenshot of this. Okay, so as b gets larger and larger, so as b gets further and further away from 0, my graph is moving further towards the left. Okay, move towards left. And what I mean is y equals x squared, my generic graph, starts to move towards the left and downwards. Okay, and as b is getting smaller and smaller and further away from 0 towards negative infinity, my graph is moving towards the right and downwards as well. Okay, so this is the impact that b has, that middle term, that middle coefficient has on our graph. Okay, b is it's kind of hard to tell exactly what your vertex will be just based on your value b. We'll talk a little bit about that later, but you can kind of see the general change that the graph is making. Okay, let's take a look at c. So if I take a look at c, I'm just going to set b equal to 0. So that means I'm talking about the function y equals x squared plus c. So that means there's no middle term now, okay? So there's just the first term and the last term. If you notice, as I slide c up, you'll notice that your graph actually just moves up, and the more negative that c becomes, it slides down. So this is actually what c is doing. C is literally just moving your graph up and down. And then the other thing that's worth noting is that if a was some other number and b was some random number, if you notice, c again just moves your graph up and down. But the interesting thing about c is that it actually represents your y-intercept, which is, if you just look at even the function and what that means, it's kind of obvious when you look at it algebraically. Like if I say I'm looking for the y-intercept, what I'm saying is I'm looking for the values of y when x is equal to 0, because that means I'm crossing the y-axis, and at that point x has to be equal to 0, right? That's along here, like x is 0 all along here. So when I'm talking about trying to find the y-intercept, that's what I'm looking for. Where does the graph cross the y-axis and that's where x is equal to 0. So here, if you take a look, this point is actually -4, and c is -4. Okay, so my y-intercept here, when I have some graph, ax squared plus bx plus c, my y-intercept will always be at 0 and whatever c is. And the reason why this is happening is because if you substitute 0 for x into ax squared plus bx plus c, you know, if I replace x with 0, then these terms will go away because it's just 0, right? And so you'll only be left with c. So that is your y-intercept. That will happen every single time. So if I'm looking at some equation and it looks like this, just based on the last video and this video, I can confidently say now that this graph, it opens downwards because a is negative, and it intersects the y-axis at -5. Okay, so I know this graph's going to look like this, and somewhere along this graph, it is going to cut through the y-axis at -5. I'm not really sure where that is, but I know that the point 0, -5 lives on this graph. Okay, so it opens downwards, and 0, -5 is a point on this quadratic function. Okay, so that's it. That is the influence that b and c have on your quadratic function. Now that you know what a, b, and c are doing to your graph, you're going to start looking at being able to identify, the vertex, which again is the lowest or highest point on your graph. It's also referred to as like your maximum, your minimum, that sort of thing. So let's just quickly talk about that real quick. So again, if I click on this, there is my vertex. Okay, I'm just going to snap a photo of this really quickly. So let's quickly talk about sort of the key things that you're going to be asked. Okay, so my y-intercept here is again at c. So this time my equation looks like this. It's y equals a is equal to 6.6 x squared plus 3.6 x minus 4. Okay, so my y-intercept is at x equals 0 and y equals -4. Okay, so that's my y-intercept. X equals 0, y equals -4. Okay, my graph opens upwards because it's my a value is positive. I can see that. And then my vertex, this is a minimum. Okay, if my graph looked like this, I would have a maximum, but I don't in this case. So I have a minimum, and my vertex, the minimum is at this point. Okay, this is your vertex. Okay, this point right here. I can also look at my axis of symmetry. My axis of symmetry, that's where the graph is being, it's almost like it looks like it's being cut in half, or it's a line where the graph can be folded over onto itself. That will always be at the vertex, right? That's always going to be at the vertex. And so your axis of symmetry is actually this blue line, which is x equals your x value at the vertex. So my axis of symmetry is at the line x equals -0.273. Okay. And the last thing I want to look at is my my x-intercepts, which I'm highlighting in yellow. In this example, they're not super obvious to see because they're going to be some decimal numbers. So I'm just going to get out of my screenshot so you can see them. So we can go back to the graph. So again, I can click on these. There they are. Those are my x-intercepts. And again, that's where the graph crosses the x-axis, right? So that means I'm looking for, so the x-intercepts are where the graph crosses the x-axis. That means that y would have to be 0, right? I'm looking for this situation, okay? And obviously that's happening right here. Those are my x-intercepts at those 2 points, okay? And usually when we talk about x-intercepts, depending on where your graph is, depending on where it's sitting on your Cartesian plane, on your grid, it may have 2 x-intercepts, like the graph we're seeing right now, it has 2. It may also just have 1 intercept. That's like when you're right here, for example, okay? So like this graph has 1, you know what? I'm just gonna set this just so it's obvious, you can see it. Like right there, right? Like that has 1 intercept, right? 1 x-intercept at 0, 0. Or your graph might have no intercept, which means it looks like that, or like that, right? Like this, where the graph actually never crosses the x-axis. So that means your graph is either below, it's either below the x-axis, right? Like the one we're seeing right now, or it might be above the x-axis like this. So the number of x-intercepts really depends on where your graph is sitting on your grid. So here's the possible options. You could have one looks like this. Okay, that means you'll have 2 of them. You'll have one graph that looks like this, which means you'll just have 1, which is right here. And that means that you'll have a graph that looks like this, which means there's none. So remember when we were talking about your discriminant, like b squared minus 4ac, okay, in the last unit, and this was telling us how many solutions x had, how many zeros existed. Remember, we could have 1 solution, 2 solutions, or no solutions. These 3 different graphs actually 100% relate to this idea. So when you have exactly 1 solution, you're talking about this graph. When you have 2 solutions, you're talking about this graph. And when you have no solutions, we're talking about this graph up here. Okay, I'm going to leave it there. And I'll see you in the next round of videos.